Okay, so I think, Neil, I'll say a few words about you before we start. It's really, I'm delighted to introduce our first speaker of this afternoon, Neil Lawrence, who is the DeepMind Professor of Machine Learning in the Department of Computer Science and Technology at the University of Cambridge. Neil's research interests are in probabilistic models with applications in computational biology, personalized health, and developing economies. Neil is extremely passionate about open data science and data science for science. And so also one of the latest childs of this passion is his Accelerate program here in Cambridge, which is an interdisciplinary research team using machine learning to advance the frontiers of science. And most recently, and this in particular, I mentioned this because of the theme of his talk and the theme of today's event, Neil has been part of the DELF group of the Royal Society, the Data Evaluation and Learning for Viral Epidemics group. And some of the research and some of the thinking that he has done along the lines of the pandemic and the demands that such a pandemic asks towards AI, towards machine learning, is what I believe he will share with us today. So the title of Neil's talk is AI Can't Fix This, Happenstance Data, Modeling, and the Covid-19 Pandemic. Very much look forward to your talk, Neil.
Thank you, Carola, and thank you for such wonderful introductions. And I guess, so to be clear, I'll be focusing more on the problems, less providing solutions. I have ideas about solutions, but I'm looking forward to others also providing some of the solutions. Is that screen sharing working okay?
Yep, works fine.
As Carola mentioned in the introduction, I'm sort of a machine learning researcher, and so that's clearly a part of the CCMI remit because of combining modeling with data. But what I want to do is start by going backwards to an old quote, and I don't want to take up too much time, so I'm not going to spend a lot of time asking the audience if they know who said this, but you tend to get things like Winston Churchill, because of course he said everything. Now this quote, there are three types of lies, damn lies, and statistics, is typically attributed to Benjamin Disraeli, but there's no evidence we can find that he actually said it. It was attributed to him by Mark Twain in around about 1900. Now, what's very important about this quote is that timing, because Disraeli died in 1881, and even if he didn't say it, Mark Twain was writing in, I think, 1904 or something like that. And I think the key part of this quote is that given that statistics was invented for the science of state, it must have been quite frustrating for prime ministers to be constantly presented with statistics that maybe misrepresented the situation. So three types of lies, damn lies, and statistics. And I'd like to substitute that for sort of perhaps the modern equivalent. There are three types of lies, damn lies, and big data, because this is the modern challenge I think we're facing in terms of where we are today with some of this. So it's kind of important to remember that mathematical statistics, and I include a picture of Pearson here, but we could include Fisher or any other number of people, was founded as a formalization to try and understand what underpinned the data and a search for some form of truth. And in particular, one of those things that came out of this era sort of 120 years ago of the foundation of mathematical statistics was things like randomized controlled trials and how you remove confounders from data and prevent yourself getting misled. Now, what I'm going to sort of, or have been arguing for some years, and I think we saw this in buckets in the pandemic, is that we're missing a new component of what I would call mathematical data science. And this is what this institute is about, and I'm sure many people will talk about today, how we bring those new techniques to the era of big data. In particular, I tend to use this term happenstance data, because in the past, if we go back 120 years, people would collect data with a scientific question in mind, whereas today, what we have is a situation where there's large amounts of data that is available, but it's not necessarily useful, and we're trying to work out how we can make use of this cheaply available happenstance data, such as location data from mobile phones, particularly in circumstances such as the pandemic. So Carola mentioned the Delve initiative, and this was very much an initiative targeted at doing this in response to the pandemic. So there's include the web page here, but Royal Society convenes data analytics group to tackle COVID-19. And I was contacted early on as a sort of machine learning researcher to help convene that group. And I should say one of the first things I did was made sure that, and you know, there was no pressure against this, that it was not just a group of data scientists or machine learning researchers. I emailed Peter Diggle at the Royal Statistical Society immediately this was coming up to get Peter on board because I knew of his sort of work and just see what he was doing in the pandemic. You'll also see that if you can read the text, it says it's a multidisciplinary group, and we got a large number of domain experts, public health experts, economists, epidemiologists, immunologists, people who were working on the front line, clinicians, all together convene around this group. And I think for me, that's one of the important things that data enables us to do. So the aim was to contribute data-driven analysis to complement the strategic response through analyzing national and international data, using emerging sources of data for new evidence, and ensuring the work of the group is coordinated with others and communicated as necessary both nationally and internationally. And the group was reporting into SAGE on a pretty much a weekly basis on questions that we were working on ourselves, but often sometimes we were asked to look at specific questions. I'll review some of the reports a bit later. So I looked at the timeline, and the first contact was sort of 3rd of April 2020. First meeting was 7th of April, and that's a meeting of the sort of group that was convening the team, and the first working group 16th of April. So everything happening very, very quickly. There's a Delve website where you can see the members of this group. And data was very much at the heart of what we were doing, trying to use data to answer policy questions and make international comparisons for input. But there were lots of challenges, particularly around getting data, which we wrote one of our reports about. Now, my own expertise is machine learning, and this is the sort of what I tend to write down when I'm trying to briefly explain what machine learning is. And I mean, you can cover a number of other areas in the mathematical sciences by this as well. But basically, as far as I see it, it's the combination of data with a model to make a prediction through computation. Now, you could also say that statistics is doing this. I think that the historical difference between, say, statistics and machine learning is statistics has worried more about the explanation of this data rather than the quality of prediction. And I think that's perfectly fine. And there's reasons why you want to do one and why you want to do others. And nowadays, I think there's a lot of actually interaction between the two fields. But that key point for me here is the data and the model are the key inputs to the system here. And I want to talk briefly about those two components and where the challenges rise from. So this is something that has been in my mind for a while, and it's what leads to my 3 types of lies, lies, damn lies, and big data, is what I call the big data paradox. Because everyone's telling us that by collecting more and more data, we're going to be able to understand more and more about the world and do greater and greater things. But as I look at the consequences of collection of this data, even pre-pandemic, it seemed to me that we understand less about what's going on. And I would give you examples such as election poll predictions, trying to work out who's going to win elections, which used to be a fairly straightforward exercise, seems to be, well, it's never been straightforward, let's be honest, but it was sort of settled at some point in my younger years, sort of about 30 years ago, and seems to become more and more difficult. Targeted medical interventions, medical stratifications, trying to understand personalized medicine, it seems to be making us sort of more confused about what the right response is. And so let me try and give you a sort of sense of, this is not a mathematical proof, I'm giving you an intuition about what's going on here. And I think exploring the mathematics of this could be quite an interesting domain. So I use this analogy. People often say that you can't see the wood for the trees. So the meaning of that expression is that, you know, you're so obsessed with the tree in front of you that you don't see the larger context of that tree, which is the forest itself. Now, what people like Pearson and Fisher and the sort of early statisticians brought us was this notion of a randomized controlled trial or a statistical survey that was randomized in some way. And that really gives us an ability to see a forest. So I tend to think of that sort of, it needs good design, but a well-designed trial gives you a really good picture of the overall situation. So one of the things we were really missing early on in the pandemic was enough randomized testing to understand how pervasive the disease was, in which age groups the disease was, And it saddened me, and I think many statisticians I spoke to, that surveillance didn't seem to be as much of a priority as it perhaps should have been for early testing. But of course, we think that as data requires. But that type of surveillance data, randomized testing, which we're doing really well now, we've got lots of great studies, both on the sort of how pervasive the disease is and also responses to disease. So I'm thinking of the REACT and recovery studies, wonderful studies. UK is really, really good at them. That is the sort of thing where we see the forest. But what I think is going on with big data is it's almost like we're in this situation here. So we're not doing the randomized control data. We're seeing the data that is around us, but we aren't collecting it in a way that is representative of perhaps the setting we want to understand, which is perhaps this clearing. What we end up with is an enormous amount of data about this branch lying on the floor here, gigabytes of data about that, but not the sort of representative data of the sort of wider ecosystem around the branch. And this is particularly challenging in this big data era because we're getting all this new information. So we think we understand more, but the information is biased, it's coming from the wrong place. And it's very, very hard for us as humans to contextualize the information we're getting. Because the truth is, and I think this goes to the heart of the paradox, is that the world is horrifically complicated. So in order to collect enough data to understand the world, you have to collect sort of way beyond what we're capable of collecting even today. So I have this notion of big data still being small. And I think that the challenge we face is we get this impression that we've got something more representative, but in reality, we've got a large amount of detail about potentially the wrong thing, and it just biases our searches. Now, I was presenting this as a sort of exec education event on Monday, and someone said, well, can we therefore just use bigger models? But unfortunately, the big data paradox is partnered by the big model paradox. So what do I mean by the big model paradox? Well, my favorite example of seeing this in action is I used to do some consulting for a Formula One team, and the Formula One team was building their simulation, their race simulation that they use on the race weekend to try and understand when they should pit stop. And they're constantly running this simulation as the race evolves and updating it. And they do lots of Monte Carlo samples in order to make these type of decisions. Now, I knew the person that wrote the simulation, and I said to them, well, how's it going? He said, well, it started out really, really well, but the simulation seems to be getting worse and worse. I said, what do you mean? Well, he said, well, at the beginning, it was giving us nice results, but as time's gone on, we are tending to get results that aren't that well calibrated with the races. And we started to talk about the problem a bit. And the example he mentioned, which has always stuck in my head as the development driver problem, was a race where their driver had been asked to pit stop, had not been asked to pit stop, because the simulation showed that if the driver had been asked to pit stop, the driver would have been stuck behind another driver. And the reason they would have been stuck behind this other driver, because it was a slower car, but it had a high top speed, and the simulation knew this. But everyone in the team who was watching the race knew that this potential driver they were going to be stuck behind was actually a development driver of the team. Now, what does that mean? It means that that driver is being paid by that big Formula One team to drive in another team for a different for a smaller Formula One team. So that driver owes some sort of fealty to the big Formula One team. So everyone knew that the driver would kind of pull to one side. So of course they went and they updated their simulation, and they added this sort of information that to use their normal overtaking model down the straight, which is a sort of probabilistic probability of overtake is associated with the difference between top speed of the two drivers, and sort of say, unless the development driver was involved. And when this development driver is involved, then you can overtake within one lap. Now, this is a very sort of common action around models, and it seems to be making the model more realistic. But it's got a serious problem, which is the change you have made is not operating at the same level of fidelity that the original model was written. So the original model is written by looking at overtake speeds and trying to see, well, what's the speed differential between two cars and what's the probability overtake, and it ignores the identity of the driver. If you go in and you start introducing, unless it's this driver, then what you do is you mess with the statistics. You're looking at information at different levels of granularity, and you're incorporating them in the same model. This is an incredibly difficult problem, and it's a particularly difficult problem when you've got epidemiologists building very, very complex models, perhaps derived from flu or other diseases, which have certain specific levels of granularity for diseases which are spread by touch, but perhaps not the level of granularity for diseases that are spread by air. So an example there would be, you may have models that do a lot on whether handshaking is occurring or not, but nothing about whether people are wearing face masks. And this was a sort of severe problem, I think, with some of the early pandemic models. So you can see it's very similar related to the big data paradox, but it's coming from our perception of what's going on in the world. We're adding more and more detail about certain aspects of the disease or the climate or whatever, but we're not always adding that sort of modeling information at the appropriate level of granularity for what the wider model is. So this is the big model paradox. And the worst thing about both of these paradoxes is that they lead to this problem. Diane Coyle did a wonderful talk that I urge you all to watch, the Fitzwilliam Foundation lecture, 9th of March, a couple of months ago. This is the YouTube link. You've got the link there. You can get access to my slides online if you search for my talks, or you can just search for Diane on the foundation lecture. And she was talking about the seeing room. The seeing room was a notion that was particularly deployed in Chile, where I think in the 1970s, when they were looking to reform their economy, and then the watchword of the day was cybernetics. Cybernetics is a sort of precursor to AI, and indeed, I would say it's the origin of my part of AI, machine learning, not classical AI. And they were trying to sort of run and manage an economy by a sort of data-driven setup. What Diane, the point she makes, and she's coming at it from a different side to me, but we come to the same conclusions, I think, is that the key issue that is missing for these big data and big model paradox is that we're losing the ability to introduce human judgment and decision-making and combine that with the type of data we have. Because as these models get bigger, as this data gets bigger, we need more and more specialism to try and understand that. And I think that that's highly problematic. The right response is actually to sort of try and go more interdisciplinary. So Diane's point, which is, I think the outcome of these two paradoxes coming together is that you might think that we can devolve more and more to the machine. But actually, I think the right response is the domain of human judgment is increasing. And she's talking about it how in firms and for the economy and so on and so forth. But this is sort of counterintuitive, that actually as we get more and more data and more models, then the need for more and more expertise and more humans to be involved is becoming greater, because it's actually harder for us to understand what that data is representing and what those models represent. She makes it beautifully in this talk. So I don't want to just talk about problems, but some of the things that I think went really well in Delve. And one of those things is what I would call data as a convener. So it turns out when you're missing a data set, that is actually really, really useful, because a conversation from a group of different experts, economists, public health, epidemiologists, statisticians, machine learners, etc., about what data they would want to answer a particular question turns out to be an excellent way of breaking down barriers between the language of these different fields, which are often massive obstacles to understanding. I sometimes argue that it's hardest for graduate statisticians and graduate machine learners to understand each other because they use the same word in a slightly different way. So it becomes very hard for them to understand each other's objectives because they're too close to each other in language. And so having a data set or talking about a data set that we would want turned out to be a really great way of bringing things together. And I do remember one of our very senior public health people had this wonderful quote where she said, well, we might not be able to do any modeling here, but we may be able to do some arithmetic. And that's the type of conversation you very often want to be having when you are trying to respond rapidly to an evolving circumstance. Arithmetic is actually often better than modeling. So this is my sort of normal thing, is what you are trying to sort of discuss across different expertises in your head. You're trying to think of what the computer says and what the data is saying, and you end up sort of arguing with each other. But this is very well known in interpersonal communication. If you can externalize your cognition in some way, you can get different people talking about things in ways that they're not talking about cross purposes. And that was something I saw working very well in Delve. So that's data as a convener, even when it doesn't exist. We're speculating about which data we wanted, really brought people together. So Delve wrote a number of reports. There was modeling in some of the test trace isolate was where we did the arithmetic, even though we couldn't do a lot of modeling, and we ended up doing simulations. There's a lot of the work here in terms of modeling work is relatively simple, sensible modeling work. It's not groundbreaking, and you can read any of these reports, the technical supplements, they're all online. They all went into Sage and had, I mean, I think after the schools report was when the government came out almost immediately saying, you know, schools is the first priority. Before that, it seemed to have been pubs that were the first priority to reopen. And that was a wonderful, Anna Vignoles was one of the leads of that report. The economics report was basically saying, look, there isn't a trade-off between health and economics, that the two are the same sort of thing. The vaccines report was trying to sort of look at different scenarios of how many vaccines we might have and what the logistics was of deploying them. And one that's close to my heart is the data report. The data report made a number of recommendations for what we should be doing as we go forward. I've mentioned some of these surveys. I think the surveillance data situation rapidly got very good. I mean, after being very poor at the beginning of the pandemic, the people did amazing work to get these studies going. But our report focused on happenstance data, this data, so to say movement data, or the types of data that are not the classical forms we look at, and trying to sort of understand how we start bringing this into daily government decision making so that we're not scrabbling around in an emergency, wondering how we make best use of this data, or trying to work out data sharing agreements with corporate entities in a rush. We need those relationships in place early. So I'll skip those a little bit and just say something about the modeling circumstance, which is not something we deployed in Delve, but just contextualizing it in another very important and urgent problem, but is less vivid than COVID, is of course the climate. So here I'm showing a climate simulation system. I'm going to use this as the basis to talk a little bit about models and what we might do here. And in a climate system, you've got a sort of, often you have an atmospheric model, a sort of land model, an ocean model, and then you may have a model of human activities. Now, to try and illustrate the sort of challenge when we get these very complex models, we need to have each of these models inputting, and these are often will be designed by separate groups using separate sort of understandings of physics to make a prediction about what the future temperature might be. Now here I'm leaning on experience from working at Amazon, where I worked in supply chain and the way they do the sort of modeling there. But what I'm showing you here is the sort of representation of the software of this system, which might be, this is what I would call a monolithic system, where each of these little pieces of code is a separate piece of code within a big box that we run on a large supercomputer in Exeter, and we get some answers out. Now, in order to deal with the challenge of the different fidelity, because of course, actually people do a lot of work to get these at the right sort of fidelity and to merge these type of things to calibrate the models. But I think we need to get a little bit more, as we look at digital twins and ways of modeling the world around us, we need to start taking that monolithic approach and turning it inside out. So in software engineering, that's known as a service-oriented architecture, where you start being explicit that each of these things is a separate component that interacts with each other in certain ways. Effectively, this is what goes on when people combine climate models together. But I think we need to get much more explicit about that and start using techniques. So how does machine learning come in and help? Well, it helps through statistical emulation, which is really originally a domain of applied mathematics and statistics. So the idea would be that we can start using machine learning models to interact with these different simulations. And the idea here is I'm showing you simulations at different granularities. So this is a low granular simulation, this is a higher granular simulation, and this is real world data. And we need to use statistical modeling to mediate between these different components and understand what they're doing. Because as we create these large monolithic models, we lose understanding of those different individual components. So that's an agenda I have, and it's kind of a focus of my research in software engineering in general, that you start being able to mirror, build a shadow system, which is a data-driven system that is allowing you to interpret and talk about the level of granularity and abstraction that you are applying within these submodels. Now, to an extent, that's largely already done in climate model, but I don't think people think about it formally in that way. And then, of course, as you go into the ocean model for itself, you see you've got all these submodels. And I think we need to do that in a sort of fractal way, start extracting those submodels themselves and applying the same treatment. Because otherwise, we're going to get this development driver problem again, that we're going to build models which are operating at different levels of granularity and therefore are poorly calibrated or need all sorts of hacks to bring them together. And if we expose the models in this way, then it becomes much easier for many scientists to look at them in the same way I described using data as a convener. We can use the service-oriented architecture as a convener. So I'm about 2 minutes over where I intended to be in time, but I'm there on my conclusions. So everything we're facing in this area and the need for rapid decision-making and rapid response is actually associated, to my mind, with the massive bandwidth constraints of human beings. We have a very limited ability to absorb data, so we're highly selective about what data we listen to. And we need techniques that get us as specialists out of that and talking in an interdisciplinary way, getting that human judgment back in that Diane Coyle talks about. The two big problems I mentioned, but they're very closely associated, big data paradox and the big model paradox, are things that are severely affecting our ability to deliver timely science at the moment. And then two of the sort of positive things I see going forward is I've already seen data working beautifully as a convener, particularly when you're talking not about the data you have, but the data you would like to have. And then this notion of decomposition of those complex models into individual components. So hopefully we can make those models a convener as well and get those interdisciplinary discussions going. And that's it. I'll stop sharing.
Thanks a lot. Thanks a lot, Neil. That was a really fascinating presentation. Thank you. So if people have questions or comments, please post them either in the chat or Q&A box. Maybe I'll start, Neil, with maybe an even higher level question to the flavor of your talk, which is, so somehow you have the model choice that you need to make, and then you also have to make a choice of how to evaluate these models. And these two things are, of course, somehow interconnected. So depending on how you evaluate the model, you'll get maybe a different model choice. So, which somehow again speaks towards what, you know, is kind of along the lines of what you've also mentioned. There's a kind of a model of all models or something like this. Yeah? So is there any way out of this loop somehow? So the model choice versus model evaluation.
It's a great way of putting it, Carol, and I think it goes right to the heart of the problem, is that any statistical modeler knows that you contextualize your modeling according to the question you've been asked. And I think that there's this quite severe problem that there's emerged this gap between what I would say is mechanistic modeling and statistical modeling. And there's a sense that when you're mechanistic modeling, you're modeling truth. Well, you are not. You are abstracting in some sense. I mean, it's like, it's statistical machine learning model. We're going all the way to one extreme in terms of our abstractions and saying, well, we'll include smoothness and something data-driven, or we'll assume linearity. And then we're being, well, statisticians in particular, careful about model verification. But if you fool yourself that you are building the right thing, if you fool yourself that you've got the physics and the mechanistics in there correctly, and you just know to go around now, and if it's wrong, I just need to make it a bigger and better model, that's highly problematic. I think that, you know, and you can see that emerging in the Formula One example, where it's clear that you aren't including all the physics, but you start including these little bits and pieces. And those choices are very specialist. And unfortunately, you know, as we've specialized in our particular domains, you know, the overall balance of which area you should invest in is not clear to me at all. Like, should I invest on the chemistry of the upper atmosphere, or a finer resolution of Navier-Stokes equations to improve my climate model? Well, everyone will say everything. We should do all of this. But fundamentally, I mean, my experience at Amazon, where we have very, very large simulations, etc., working together, is actually what you really need is a very flexible ecosystem and some way of objective judging. So the idea here is to sort of bring in the statistical modeling, the verification of what's going on, as a sort of judge, as a referee between those different component parts, so that we're not having an argument between different domains saying we need to invest in this supercomputer for Navier-Stokes, but we're actually saying, well, statistically speaking, for this question we care about, it seems that the highest sensitivity in our system is to this component, and that's where we need to put our work. Instead of that being done, I'm not an expert enough on it, but I feel that isn't being treated as a science enough now, and that's where we need to correct things.
Yeah. Okay. I totally agree. That's really interesting. So there is another question from Philip Sellers, who asks, so question for Neil, does he have any thoughts on the rapid growth in computational requirements for models and what that might mean for their development in rapid situations?
It's a great question, and I think it also relates to this to your question, Carol, because there's this sort of this issue of accuracy, there's this issue of computation, and I think that you know, I really think it's interesting to look at humans ourselves and see how we respond differently when we're asked different questions. Like if someone starts punching me in the face, I don't pause and calculate the precise trajectory of the incoming fist. I move my head out of the way, and there's very little compute involved in that, right? And that's telling you the context the situation requires you to do different amount of computation. And I think the worry I have, Philip, is that we don't have that dial. We don't have the dial to shift the computation up or shift it down and get what we would consider, so like the difference between the detailed mechanistic model of exactly what's going on in the car and the physics of the aerodynamics as they're overtaking versus this is what we've seen over a number of races that the overtaking result is, that statistical component. And by decomposition of the models, it's just the first step to start getting clever about how we'd introduce that, because coming back to Carola's question, the right answer is totally contextual. That depends on the question you're asked, which one of those things you want to do. And we're just nowhere near sophisticated enough about that, I think, to do anything like we claim what we're going to do with digital twins, et cetera, et cetera.
Also, actually, how well, even if you know what the question is, how well can you evaluate whether you actually answered it well? That's a big question. I mean, I'm coming from imaging. This is a big question in image analysis. Image denoising, quality measures for images, not at all clear what is good, how to capture really visual perception.
Scientists, we're also not often put, I mean, that's what's really interesting when you go and do policy advice. You're not put regularly enough in the situation where the answer is needed on the short term. I mean, some of the things I think scientists said in the pandemic have just been embarrassing. If you look at anything in terms of what the government has to do in terms of making a decision. I mean, you can complain about the government as much as you like. There's lots to complain about there, but I think we should focus on where we're going wrong, and coming up with the right answer 8 months after the decision is made is not good enough, right? The decision, we need to get the best answer from the information we have available at the time. And I think we need scientists much more closely involved in that process so that they understand what the limitations are and can make realistic suggestions for what the solutions might be.
Right. Okay, so there are more questions, but I think in the interest of time, Neil, if you agree, because there is a coffee break afterwards, please, Sally Levesley and Max Sondag, please remember your questions, and then we can engage more with Neil. Then if you can stay for a bit longer, Neil.
Yeah, sure.
Okay. Okay, super, thank you. Thanks a lot again, Neil.
Thank you for the invite, Carola.
Thank you. All right, so our next speaker, Ronojoy, are you here? Yes. Oh yes, I can see you. Very nice. Good. All right.